yeah, I'll maybe, just give my kind of quick reaction to the question about, using high resolution topography and numerical methods. And, to me, it was really the idea of different dimensionalities of, sort of 2.5D to full 3D, and then even 4D. So it kind of could change. And then we know that the topography acts as both initial and boundary conditions, and it's something we can use to test our models. So I'm going to talk just to kind of give a little bit of maybe a narrow perspective on numerical models and some applications from high resolution topography, and then somewhat, I hope, complementary to what Irina presented the other day. And then I'll give just a couple points about high performance computing lessons from OpenTopo that might be lessons for us as we would move forward to try to bring data and models together, and a couple of concluding thoughts. So when I was when I think about numerical methods, this is what I was thinking about: is sort of solving differential equations in a numerical sense. And so this is some work I admire of Josh's, where he was basically solving this equation for the evolution of the landscape, mostly looking at kind of finding a solution to mass conservation with a specified set of transport laws run for 500,000 years. And those transport laws are sort of governing hill slope processes. And in this case, and there's no fluvial or debris flow processes. And so he used high resolution topography as kind of an initial condition. So up at the upper left, and then he evolved that initial condition forward using these different rules for how the soil material fluxed down the hill slope, and was able to kind of show how maybe different rules were more appropriate as far as their correspondence with the landscape. And so there was initial conditions, and then that kind of compares with the character of the morphologic relationship. And I always like one thing that Josh was talking about, sort of the inappropriateness of the sort of linear diffusion and the sort of pumping up of the landscape like a balloon. So clearly that didn't work, whereas this one that had nonlinear dependence on slope as well as soil thickness worked better. So that's what I was thinking of, at least initially. Here's another one. Sorry that little thing's in the way there, but it says hydrologic modeling using high resolution terrain and vegetation maps allows unprecedented details on spatial patterns of runoff, soil moisture, and evapotranspiration. So this is something from the person next door to me in our building at ASU, from Enrique Vivone and his student Adam Shiner-McGraw. And they used the high resolution topography and also high resolution imagery for this little catchment, this experimental catchment in southern New Mexico. And we're able to, by sort of setting up the model with topography and vegetation and their sort of 1 meter Voronoi mesh that defines the top of these soil prisms, they could solve the sort of full hydrologic problem that basically explored the changing sort of properties of the conductivity of the hill slopes and sort of the trade-off between runoff that's generated directly from the hill slopes or more following percolation. And so this, I wanted to show this because it's more than just the kind of treating the topography as a single interface. It's also what's underneath that material, the soil, and then the need for additional information, including the vegetation. And there's a kind of a nice section of this paper, confronting numerical simulations with field-derived conceptual models. So the key issue here is scale, that we have the observations of the topography and other features at the scale at which the processes are operating. So here's another one. Now, one of the things we see is, especially at these high spatial resolutions, is application of computational fluid dynamics tools to certain surface process questions. So these are solving Navier-Stokes equations and large eddy simulation approaches. And so this is from another colleague at ASU, Ian Walker, and his colleague Sad here. And this is for aeolian applications. So we're starting to see the CFD increasingly use to model flow over aeolian landscapes, including natural 3D ones. And it's used to extend the empirical observations that they might have from the field of, let's say, an array of wind or sediment transport sensors, and kind of get different views, let's say different ranges of incidence flows, and then also basically validate the computed sediment transport by differencing with repeat surveys. And that's that they have 8 surveys now, or 8 years of data coming from the Cape Cod work. And one of the points that Ian mentioned was that there's this kind of roughness parameterization, quite accessible with the high resolution data, but it really controls the shear stress accuracy. And so, how do we deal with the vegetation and the bed form? You can see them in this calculation. This shows the wind speed at the surface, so it's really controlling the shear stress. And then it has also the wind direction, like a little vectors. And then he said, it's sort of like a taste of the high resolution data, but then you want more because we need to have data before and after various events, and to kind of explore a broader range of magnitude frequency relationships. Here's another one. This is super cool. This is from Roman DiBiase at Penn State and his colleagues, where he's using structure from motion models of a channel bed as kind of a basis for the boundary condition for CFD models of the flow and sediment transport. And so this is, you see a really beautiful model of this channel floor, and then that SFM model takes a fair amount of cleaning. So this is one of our needs to get it into OpenFOAM, which is one of the big tools for solving these CFD problems. But once that's in, then it's possible to compute flow lines and velocity profiles. So this is really exciting to have this work in review, and I think it's quite interesting to see it coming. So then another CFD example. This is from another person. Kind of had to reach out quickly to my friends and neighbors. So this is Mark Schmeckley at ASU, just using, this is more CFD, but this is the past Eddy simulation, where they're using LiDAR topography and also high resolution bathymetry from the Colorado River as a boundary condition for these really detailed CFD calculations for turbulence, which then obviously significantly controls sediment transport, which has the application in the Grand Canyon for refreshing the beaches. And so they had to solve both the flow as well as the water surface position and velocities. And so this quite rich model result is at or even finer than the discretization from the topography itself. So here's an application. That little thing is kind of annoyingly in the way. It says hydrodynamics to assess debris flow hazard in complex urban topography. So this is another colleague, Jeremy Phillips from University of Bristol, who's a volcanologist and experimentalist. And what he was showing, there's a little video that didn't play. Crap. Well, the exciting part of this is not shown, but what they were doing is doing hydrodynamic calculations to look at mud flow propagation through complex topography, which in this case is a city. This is definitely where we need high resolution topography, because the topography is dynamic because of construction and destruction in the urban system, and so they had to force the computations by that topography, and they used this as a tool to communicate with the local community and say, look at what could happen. And so that, they said, was quite effective as far as the kind of community outreach and anticipating hazards. So here's one. This is from Joe Wheaton. This is hydrodynamics with ecological implications. And I thought this was really cool because it allows us to explore parameters of interest, let's say ecologically, like if you were a salmonid, where would you want to hang out in the river? And so you compute something like net range of energy intake, and you can go, instead of having a sensor or actually having the fish, we can sort of compute what this parameter would look like everywhere in the system. So they use Delft 3D they've got it working so they can really hammer it with multiple simulations to really explore the parameter space in a pretty automated way. One point they made was that the mesh preparation is really one of the big challenges and a big need. So then moving on to the lessons from open topography, we don't have numerical methods per se running in OpenTopo, but we are computing these higher level data products, which would be the sort of required input for many models. And a couple lessons. So the first one is this effective energy and mass transfer, which was something developed by Tyson Swetnam. So we're working in collaboration with him, and it runs on the supercomputer resources, both at San Diego Supercomputer Center as well as on the EE network and Open Science Grid. But this tool basically computes the monthly global solar irradiation and hours of sunlight, which we know is a critical control for many ecological and geomorphic processes. So another thing that we run in that's a little bit more mature in OpenTopo is using TOWDEM. So hydrologic analysis for terrain data is a critical input for many numerical methods, flood routing and landscape evolution, as we just heard. And so here we partnered with David Tarboton to take what was a desktop tool and put it into production and high performance computing, and that was not trivial. And so that's one of the lessons, is that you know, I think Joe said it also, is you have something worked on your desktop in your group, maybe with your data, but making it kind of be sort of pretty bulletproof for a production situation takes quite a bit more work in terms of the developer time and having experts that know how to sort of make these tools function in a wide range of demanding and unexpected user conditions. But now that it's working, we've had 17,000 jobs run, and people are invoking, you know, this high performance computing on their data. But the lesson is really another need is staff support. So now this is something for Bill. This is really kind of influential in my thinking as I've come back to it over the years. But what this says is, what realism do we need from our data and models? And so with one thing you could think of is the high resolution topography is so good, it's like this detailed realism. It's like a computer, like a picture of the place in the computer. But is that really what we need? You know, or are we okay with the statistical realism, the lower left, where it's not exactly all the spatial relationships or other functional relationships, but the key aspects of the phenomena are coming out. And then, of course, we can have something that's apparently real, but totally not something we would experience in this Earth, maybe in other exoplanets they would exist. And then finally, we might have this essential realism where it's a little cloudy here and there, but we got the main point, and it does the job as far as answering the questions we may have. So I think this is really powerful. It's also coming from this paper, which reminds us that the numerical methods we need for prediction. We use them to predict something, but what is it that we want to predict? How much of what we want to predict do we need? And so this gives us a little bit of a vocabulary, I think, that is extremely helpful. So then concluding thoughts. So, you know, what good are models? So if you go back to this Oreskes paper, you know, they're kind of actually pretty skeptical in some ways about how far we can go. And now, you know, 20 or 30 years later, we know that models are powerful, and they're actually easier and easier to use and deploy. But we have to be careful. You know, we know that they let us build intuition on a quantitative and physical basis. We can corroborate hypotheses, check for discrepancies. We can make these parameter sweeps through a whole range of values and see what might be most sensitive as far as a question that we have, and then explore what-if questions. But, you know, is the resolution always necessary for the question? One of the things that you know, I'm not really a modeler, but one thing I really appreciate is the power of abstraction. So, you know, we can sort of reduce the question to a very simple one, which is not what's happening if we have full 3D, super high resolution, multi-process models. we might sort of lose some of the power of that abstraction. So needs and gaps, we need the multi-scale approaches. We can't do high resolution everywhere all the time. So what are the ways to scale up? The meshing seems like actually a fairly practical need. You know, would it be a question that the community would have to say, all right, we need to have open topo, you could push a button and you could get a mesh that would be a Delft 3D mesh right out of the calculation. You know, the uncertainty still is important because if we use these topography as a boundary initial condition and it has a bunch of noise in it, that noise basically influences the model. We need training and tool curation, common interface and standards. We need to know about HPC access and integration. So CMS, open topography, other infrastructure, and then that need to sort of be able to take these tools from the desktop to the cloud and HPC and back. We need the technical staff support. We need these validation sites and data sets. We still need to be able to test models against each other and against data in sort of a coherent way where we really understand what's going on. And in the terms of the rescues, the validation is kind of this establishment of legitimacy for a model or a data set. And then, you know, I don't want to sound too pessimistic because, you know, the numerical methods as we've advanced them really give this opportunity, but also a challenge to go beyond steady in time and homogeneous in space, but we have at the same time the problem of increasing ambiguity. You know, is it what's really causing that change? Because we have so many knobs to turn. And so we have these, you know, beautiful tools, but we just need to make sure we know what's under the hood. So that's my story, and hopefully there's some thoughts and people may want to add comments.
I was going to ask one because Ramón always asks the first question.
Yeah.
So first off, I don't know why you were second choice, Ramón.
Thanks.
My question is kind of, and maybe this is to everybody, but we use the term high resolution. What would you define high resolution as?
Well, that's a great question, and we saw, you know, I mean, the quick answer is, in my mind, these days, I say it's a meter or finer scale. But that's mostly because that's, in a way, that's where most of the data are, especially most of the airborne data, as we can kind of represent them at about a meter. A lot of important phenomena are at a meter scale with scale breaks around a meter, at least phenomena that maybe I'm interested in. But I noticed, for example, Irina, some of the finest scales you talked about were down about 15 meters. And that's quite fine, I'm sure, for your team. But then if we go to the Roman DiBiase sort of representation of those bed forms or the sand aeolian cases, the fine, you know, it's finer than that. So I remember at the workshop we had with you last year, we tried actually to correct ourselves and start saying it's not high resolution topography, it's meter scale topography, or it's decimeter scale topography, or decameter scale topography. So I don't know if we should start to change our sort of nomenclature a little bit to kind of not have some of these semantic collisions of is my high resolution topography the same as yours.
You start talking across disciplines, everybody has a different. So when you start saying we need high resolution topography, if you're working with themselves,
definitely. Thank you. Somebody else had a comment or?
Good question. I think related a little bit to the mesh problem. When you're doing numerical modeling, one of the first things you want to add is sort of where's ground. You want to build hydrodynamic. But one thing that seems like high resolution. But talking about high resolution data can get you is also drop. Sort of some people might call it upgrid portion that's above the base level for the grid. So it's not only, it seems like there's a lot to be learned, I think, vegetation in particular.
Right. Or in the urban cases, which becomes more and more of an application with vehicles and permeability of flows going under a car. No, it's key. It's I think a really interesting opportunity and something we heard a lot about. Roughness parameterization and general opportunity. I think Josh, you showed it. Your student had this interesting characterization of roughness, which was the land surface and nearby elements that would control the flow. But it, like she had sort of mowed it at about a meter elevation above the ground surface. So I think that's a really exciting place to go. But then in the models, then still, is it a sort of infinitely impermeable boundary? It just happens to be quite intricate in its shape, or do we give additional properties to those boundaries?
So you had kind of touched on this idea of validation models, right? And I'm curious what you think about kind of the status of field measurement. What we can measure in terms of actually happening in the process. So I'm coming from field geomorphology, and we've had people kind of run these really, really intense CFD 3D models. And it's beautiful, it's amazing, it's so much dense data. And so I would say the ability for this obtain high-res topography and the ability to model that is increasing kind of like exponentially. But the tools we have in the field to actually try to measure those are maybe increasing like linearly, if that, right? So commonly in rivers, we use acoustic Doppler loss emitters, and we've been doing that for over 20 years, right? Probably even more. So can you comment on how you maybe try to reconcile that issue with the ability to get this amazing result from a model, but maybe in the future not being able to actually get it in real life?
Yeah, well, not being a serious field sensor, take this comment with some grain of salt, but the numerical methods let us maybe do some optimization for positioning of sensors and the observations that need to be made. I think that just like all the other technology that's advancing, that sort of micro electrical sensing, these tiny sensors on chips is a really big potential, because they're cheap, low power, and easy to deploy. So I imagine what would be really cool is to have a drone kind of fly over a landscape, and while it's taking its pictures, it's also dropping these little sensors, and they're kind of situating themselves within that system and making observations. And then the drone comes back a few days later and pulls all the data off by through a low power Bluetooth connection. So that's one way, which is kind of a large N set of observations. I think at the same time, sort of really high quality, dedicated observing needs to be done as well. But maybe, there are other people in Europe who are big observers, so maybe they have some comments.
Thank you for a really nice talk, Ramón. I enjoyed it. Just like a whole bunch of different examples yet again that are like out there in the one comment that I had is I feel the models are like sort of a fluid flow, like green transfer, they're so rapid green independent that it becomes important to have high resolution topography for prediction. And the example that triggered that thought was that the free flow in a city kind of prediction, right? Where like if something matters to people where their house is there and doesn't the flow that doesn't affect it, and then you have a different game that's followed or not. Do we learn about the free flow in general from such a small that high resolution? I'm not sure. I don't think so that much. So that's interesting that there's these different things about like, do we learn about processes, or do we want to make a like global prediction of like how big the model is? And the other one was where Joe had been talking about this, the heterogeneity in the river at high resolution characterized for fish that or not, whether it's like a record pattern or not. And there you can see that like once you've got the different classes, you can tell something about the whole position. Again, you don't need to say those are just problems. When you hire needed upskill for whole system, figured out how it works.
Yeah, this one here, it's the pity that what we don't see is just a evolving debris flow thickness as it moves down slope through the complex urban environment. And I think your point is quite interesting because, you know, it's not the most cutting edge, super perfect hydrodynamic model of debris flows, but it's quite adequate as far as describing that phenomena, in particular for the application of understanding what's going on in that town. Yeah.
One last one. Very nice talk. So my question is, most of the topography technology that we're talking about here is much larger scale than most of the numerical model can simulate, especially if we're looking like high resolution in the model, like station movement with water depth change, then it's relatively smaller scale than the landscape scale. So my question is, how powerful do you think the numerical model can be to predict the real landscape, especially in a higher resolution?
Great question, and I think it goes to you know, some different strategies. We can continue kind of the brute force approach, which is try to do everything everywhere as best we can. But I think there's some clever sort of multi-scale approaches. So using some models at very fine scales that then sort of operate within their little box and sort of hand off at the boundaries of that box to another set of boxes at a coarser scale. I think also the power of the abstraction of the models, maybe we don't need to solve all of the questions of the phenomena, but just the essential ones. Of course, that's what the scientists have to figure out. But I think it's a great philosophical question for us for the breakout.
Thank you.
That's great. Making a lot of cool stuff. Thanks for that. Just a side point on the comment about the computational mesh. Right, you did make the point that a lot of time often goes into building computational meshes, but in this particular application, we've got 5,000 of these automated because we're just taking advantage of dumbed down, simple rectilinear meshes, raster meshes. So the computational mesh generation is fully automated, which we couldn't get away with topography. We have high resolution topography, and we aren't so limited on computational resources. It's not that big of a deal to just use a simpler computational mesh and then let the topography for the rest of it. So it's kind of a nice sort of bonus of now having access to all the high resolution topographic data, but that doesn't take away from the point that we don't necessarily need to do this everywhere. Use that upscale clever. That's not contradictory.
No, that's super helpful. Actually, I hadn't quite appreciated that you can have a simpler mesh if it's really fine, as opposed to some really elaborate triangulated mesh that's trying to solve a whole bunch of data gap problems.
That's